In this video, we're going to be going over solving rational equations. I'm on page 3 of the note pack. Now, you worked with solving rational equations actually back in Algebra 1 and in Algebra 2 and also actually in FS. So we're going to be looking at some similar equations that you worked with previously. Now, we had rational functions on the previous 2 pages where we were graphing rational functions to see how the graph appeared on a screen. However, this time we're actually having equations where I have the function set equal to 0. So now I'm looking for what values of x, or if any, will make this equation hold true. Now, when we have rational equations like this, remember the rational meaning that we have a polynomial in the denominator of an equation. When we have rational equations, we will have to watch out for extraneous solutions. Remember, sometimes when we solve equations like this, we end up getting values that we think work, but actually cause the denominator to turn to 0, which actually make the fraction undefined. So we'll have to keep that in mind, but we check that at the end. A few different ways to solve the equation. One technique that I would suggest that you use is the idea of taking your equation and multiplying the entire equation by any factor that will cancel out your denominator. For our case, if we multiply the entire function through by x minus 4, that will clear out this one denominator that we don't want. Remember to distribute through to all the different terms, though. So when I distribute here, I have x times x minus 4. Normally I would distribute that through, but I'm just going to write down what I get once I distribute the x minus 4 through, and then I'll take care of the other distributing afterwards. Secondly, I have 1 times this factor, and the x minus 4's will cancel. And then the x minus 4 times 0 will give me 0. Now I can see that this is going to end up being a quadratic. Typically on a quadratic, when I'm given something like this, I like to try to factor it, but I can see that x minus 1 and x minus 1 would be the only ways to factor this over the set of integers, and that's not going to give me the appropriate middle term. So I know I'm going to have to use quadratic formula. I'll go up here. So I know x is going to equal 4 plus or minus square root of the b squared minus the 4 times a times c all over 2a. And when I simplify that, I get 4 plus or minus the square root of 12. I'm going to rewrite 12 as 4 times 3. And definitely at this level, you need to simplify these radicals down and give the exact value for solutions in the most simple form. Whoops, made a mistake. So I have 4 plus or minus 2 times the square root of 3. And both these are over 2, but I'm going to split it up into 2 fractions since they will both reduce down. So I get my solutions of x equals 2 plus or minus the square root of 3. Now, as I said earlier, we do want to check for extraneous solutions, so I'm going to check. And remember, if I plug 2 plus square root of 3 in place of x here, I'm not going to create a division by 0. Nor if I plug in 2 minus the square root of 3, am I going to create a division by 0. So if I check these on my calculator or check these longhand, I'll find out that plugging in either 2 plus square root of 3 or 2 minus the square root of 3 will both be solutions to this equation. So neither is extraneous. Now when we move down to number 2, you can see now my fractional values are a little more complicated, but I have 3 fractions that I'm adding together, and I want the sum of those 3 to equal 0. Once again, I have the possibility of having extraneous solutions after I go through and solve. Now, factor any denominators down that aren't all the way factored. That will cause you to get the least common denominator when you look for a multiplier to get rid of your denominators. So I'm going to factor out that common factor of x on that third fraction. And now I can more easily see what I need to multiply by in order to clear out my denominator. So I have three different denominators. However, if I multiply everyone through by x times x plus 2, I can clear out all of the denominators and I'll just have an integer type of expression that I can then solve. Make sure you distribute the x times x plus 2 to each of these three fractions on the left side of the equation and also to 0, which we know is going to end up being 0 on that side. On the first distributing, the x times x plus 2, the x's will drop out and I'm going to have x plus 2 times x minus 3. When I distribute the x times x plus 2 to the second fraction, the x plus 2's will cancel and I'll have 3 times x. For the third fraction, multiplying through by x times x plus 2, the x times x plus 2 will cancel out both top and bottom, and I'm going to be left with 6. And then, this being a 0, we know that the product is 0 here, but if this is a number different from 0, make sure you would distribute that through to that term as well. When I multiply this out, I end up getting x squared minus x minus 6 plus 3x plus 6 equals 0. Again, simplifying, I can see that I'm going to end up with a quadratic. My 6's cancel out, and I end up with x squared plus 2x equals 0. It's a quadratic. I can do some factoring, though, to find my solutions. And I end up finding that x equals 0 and x equals negative 2 are two solutions. However, I need to check for extraneous. And I find out that if I use 0, I make my first fraction have division by 0. And if I use negative 2, I have my second fraction have division by 0. So although two of these two solutions appear to be answers to my equation, neither one of them actually can be used in the original equation. They make me have division by 0 in really all three of these fractions. So my actual answer is there is no solution to this equation. Now the third example that I have on our note pack is dealing with an application question that is dealing with a mixture question. And I have how much pure acid must be added to 50 milliliters of a 35% acid solution to produce a mixture that is 75% acid. So picture-wise, think this is the idea. I have a container that holds some pure acid. So it's 100% acid. And how much of it I have, it's an indefinite amount. Because whatever amount I need, I will get. And I'm going to add and pour that into a container that has 35% acid solution in it, and I have 50 milliliters. So I have 50 milliliters of an acid solution that is 35% acid. The other part is water. And I want to end up producing, once I pour some acid in here, I want to produce a new solution that is going to end up having a 75% acid solution. So I want to increase the acidity of this solution, and I want it to be perfectly proportioned in such a way that once I pour this pure acid in, I want to end up having 75% of this is acid and 25% is water. Now, I don't know how much I'm going to add in. I'll say X is the amount of pure acid I'm going to add in. And when I add that acid, I know I'm going to end up with, I had 50 milliliters of the 35% solution, I know I'm going to end up with 50 milliliters plus X is going to be the amount of 75% solution in the end. So I'm going to have X milliliters of this that I'm going to add to the 50 milliliters of that, and once I do that, it's going to end up that my solution is going to be 75% acid and 25% water. So how do I have that mixture set up? Well, I know that when I make solutions, that I want the end solution to end up have 50 milliliters plus X. That's how much of my solution I'm going to have in my beaker at the end. Now, to figure out the concentration for the acid, I have to take how much acid I have, which is going to be in a liquid form, out of how much total solution I have. So my numerator has to be the amount of acid, and the denominator has to be the total amount of solution. The amount of acid I have is all controlled by this X milliliters of pure acid that I'm going to put in. So when I take my 100%, put it as a decimal, 1 times X, that's the amount of acid that's going to come from this beaker. Plus, this beaker actually has a specific amount of acid. 35% of my 50 milliliters is acid. This comes out to be 17.5 milliliters. So I have 17.5 milliliters in this beaker is pure acid, and then the other remaining, let's see, that would be 32.5 milliliters is actually water. And so when I want to figure out an equation to describe what's going to be in my third beaker, I know that the amount of acid I have is, this is coming from the pure acid, this is coming from my beaker of the 35% acid, that's the amount that's actual acid. Amount of acid divided by total solution needs to be 75%. So now if I solve that equation, I can determine what my X value is so that this beaker will have the 75% solution. So this is my equation. Now I can solve that equation by multiplying both sides of the equation by 50 milliliters plus X. When I do that and distribute it to this side, I end up with X plus 17.5 milliliters. And when I multiply the right side of the equation, the 50 milliliters times X, I end up with 37.5 milliliters plus 0.75 X. I'm going to skip some of the algebra. Once I go through and end up solving for X, I end up getting X is equal to 80 milliliters. So if I have 80 milliliters of pure acid, and I pour that into the 50 milliliters of 35% acid solution, naturally the concentration of the acid is going to go up because the other I'm adding is 100%. And if I add 80 milliliters in, I'll end up with exactly 75% acid solution. And I'll really end up with 50 plus 80, 130 milliliters of acid. And that's it for page 3.